Hello, welcome to Lecture 5, Application of Newton's Laws. This week we're going to look at introducing more dynamic force problems and combine our understanding of kinematics, which is the equations of motions type problems, and dynamics, which is our forces problems, to solve more interesting scenarios. When we look at applying Newton's laws, we are going to take our understanding of forces and solve motion problems that apply those forces. We need to focus on one key distinction. We will need to consider whether we are in an equilibrium phase, where we have a net force equal to zero, and thus a constant velocity, or whether we're in a non-equilibrium phase, where we have a net force, and thus we have non-constant velocity. To make this determination, we are considering Newton's second law, where the sum of all forces is equal to the mass times the acceleration. As we move through this chapter, we'll introduce new types of problems. To make these problems more simple, we will apply the following base assumptions. Anytime we have a pulley, rope, string, or wire, we're going to remove the effects. These objects are assumed to have no mass and encounter no friction. This is not realistic, as in reality, these objects reduce the efficiency of any system by adding mass to the system or incurring a penalty to efficiency through friction. We will continue to reinforce our practice of applying a systematic approach to problem solving. For each of these problems, you should consider the following steps. Start by drawing free body diagrams. We know how to do these. We've done these for the last type of problem. The new part is that we may require more than one free body diagram. This could be because we have more than one body, or we have more than one phase. The next two steps could happen in either order. Some problems will be beneficial to work in the order written, and some problems will be beneficial to work in the opposite order. Overall, we need to identify the components and equations of force. By components, we mean all types of forces and their directions. And by equations, we're referring to our sum of all forces is equal to the mass times the acceleration. Something to pay attention to is that this sum of all forces is going to be replaced by each of the forces acting on the body. We'll look at that in more detail in a moment. For identifying the components and equations of motion, we are applying Chapter 2 content. Often the connection between these two steps will be acceleration. We are going to discuss several problem scenarios in this chapter. In each case, the common factor here is that we will need a system of equations. Recall that we need one equation for every unknown that we have to solve. And through this chapter, we'll see two methods of accomplishing this task. Once all of our setup is complete, we'll need to substitute all of our known values and evaluate for the characteristic we want to solve. It's important to remember that because these problems are quite complex, we need to also complete the final statement segment of our solution. You need to interpret what the value is that you just solved for. Our first level of problem is to consider an object with an applied force and a force due to friction. So consider this. You are pushing a child on a sled at a velocity of 1.7 meters per second and applying a force of 50 newtons. If the sled and child have a mass of 25 kilograms and experience a frictional force of 60 newtons, how far will the child and sled travel? Our first step is to consider the free body diagram. We have ground, we have a sled with a child on it. Because the sled and child have a mass, they will have a weight. And because they're in contact with the ground, they'll experience a normal force. We are applying a force of 50 newtons, and the child and sled experience a frictional force of 60 newtons. We should also note that this is a two-dimensional problem, so we should apply our positive axes. So we will choose up as positive y, and we will choose right as positive x. Our next step is to consider forces. This problem asks us how far will the child travel. which means we're going to begin with a scenario where we actually consider motion before forces. We can note that there's an initial velocity of 1.7 meters per second. We've been asked to find delta x, and because we have no time frame here, we must assume the only thing that's going to stop increasing that delta x is the fact that the child will come to a rest. In that case, we expect to see an acceleration, which means we expect a non-equilibrium problem, and we expect to see a net force, which we do, as the force of friction is not equal and opposite to our force applied. So considering our motion equations, we have a velocity initial, a velocity final. We know an acceleration exists, and we want a displacement. This sounds like the type of problem where we use this equation, and we can rearrange for the quantity we want. Note that we have a quantity we're interested in and an unknown quantity, so we will need a second equation. At this point, we'll switch over to our consideration of forces. So we begin by using Newton's second law. We want this acceleration value so that we can substitute it into our motion equation, but before we can get there, we need to replace the sum of forces with each of the forces acting on our body. So this is the force of friction and the force applied. And we can rearrange. And now we have an equation to remove the one unknown value from our motion equation. So we'll set up our system of equations. As we work through substituting our values, it's important to consider the direction of each of these. Our force applied lines up with our positive x. Our force of friction is with our negative x. We need to include those signs. Similarly, we begin with what must be assumed to be a positive velocity. So we'll keep a positive sign when we input that. And substituting and calculating all in one step, we should get a numerical result of 3.6125. And our units are meters. And the child will travel approximately 3.6 meters before coming to a stop. Some notable things from this problem. We had two unknowns and required two equations. And we applied the substitution method. As an alternative to substituting, you could have considered solving the motion equation for acceleration as well, and then setting the two equations equal to each other. In this chapter, we can consider problems that are slightly more difficult by combining applied forces, friction forces, and ramps. So consider a Tesla Model Y parked on an icy hill with an incline of 8.5 degrees. The coefficient of static friction for rubber on ice is 0.15. If the gross vehicle mass is 2,405 kilograms, will this car remain in place? Again, we consider the free body diagram. So we know we have a ramp with an angle of 8.5 degrees. On that ramp, we can place our Model Y. Again, because that car has mass, it will have weight, and our weight's going to apply directly down. This means that it'll have a component that is directly into the ramp and a component that is along the ramp. Recall from our previous unit that it simplifies the equations if we make the y direction perpendicular to the ramp and we make the x direction along the ramp. Which means if we consider the angle inside of this triangle is equal to theta, that gives us an applied angle equal to 261.5 degrees. That's 270 degrees minus theta. Remember, to get the component of a force that's applied on an angle in the y direction, we calculate the magnitude of that force multiplied by the sine of the angle, measured all the way back to the x-axis. And to get the x component of that force, we take the magnitude of the force and multiply by the cosine of the angle all the way back to the positive x-axis. The car will also have a normal force. The normal force is perpendicular to the ramp. We do not expect the car to leave the ramp, so we know that it will be equal and opposite to the y component of the weight. And we're given a coefficient of friction, which means we can assume that frictional forces will apply. Remember, friction always opposes motion, and in this case, our unbalanced motion is trying to take us down the ramp. So this will let us determine that our friction will be applying up the ramp. Friction is tricky. The force of friction is based on a magnitude of mu, in this case static, multiplied by the magnitude of the normal force, which in this case gives us the negative mass times gravity times sine of 265. When we combine that with our coefficient of friction, we have an equation that ends up looking like this. We have no other forces acting on our object, so this is the end of the free body diagram phase. Our second phase is to consider all of the force equations. Remember, a large portion of understanding physics problems is being able to understand what question we're being asked. If we're asked if the car will remain in place and it is currently parked, then the motion portion of this problem is just asking, is there an acceleration? In other words, is this system in equilibrium? So we can solve the whole problem by looking at force. Again, we start with the sum of all forces, which is a vector equation, which means we should consider our y components and x components separately. But remember, we don't expect the car to leave the hill, so we know that our force normal is equal and opposite to our force of weight into the ramp. So we know that this portion, or the y direction, is in equilibrium, and we can focus solely on our x component. So this means we can look at the information given, and we know that the sum of the forces will be the force of friction added to the weight in the x direction. And this will give us information about our mass and acceleration. If we substitute what we know about our force of friction and our weight in the x direction, we have an equation, and we can see that both terms on the left-hand side have m and g, and the term on the right-hand side has m. So if we factor these two terms out and divide this over, we can make this equation a little bit more manageable. Recall that when we complete this factoring step, what we're realizing is that if we expand these brackets, that means we would multiply m and g against both terms, which would take us back to what this looks like. It's a way of minimizing the amount of times we have to write the same variable. One of the advantages of taking this step is that we recognize there's a component of mass on the top and the bottom, so we can also simplify those out, making the information we have to enter in our calculator more straightforward. So now if I substitute all of my known values, you'll see that when I substituted for g, I only used the magnitude of g. Similarly, everywhere I've written g, I've only ever written the magnitude symbol. This is because it's showing up from the magnitude of the weight, which we got from our vector decomposition. It's important to know that when we take apart the vector into its components, the direction is handled by the angle and trig function. So we only ever use the size of our force, meaning we would only ever use the size of acceleration due to gravity. Now, when we plug all of this into our calculator should come back with a fairly specific result of 0.0053219090. So this is a positive value in the x direction, suggesting that the car is accelerating up the hill. This is why it's really important to complete a final statement to answer our question. While we have a numerical value, it represents a situation that does not connect with reality. Friction is a reactionary force, which means it cannot increase the magnitude of velocity. This calculation is best thought of a maximum amount of friction. So that is the amount of friction we must overcome in order to have enough force applied to accelerate. So for our interpretation of this result, we say that yes, the car will remain stationary. Take a moment to consolidate those two new insights on friction. It's very important that you consider these moving forward. In that same scenario, what were to happen if a careless pedestrian bumped into the car, giving it a velocity of 0.10 meters per second down the hill? The coefficient of kinetic friction between ice and rubber is actually the same as the coefficient of static friction. Here we're asking you, will the car reach the bottom of the hill if it's 12 meters along the ramp? Our first two stages, the free body diagram and our consideration of forces, are very similar to the previous problem. So we're going to reproduce those. The only change that we're going to make is that we now have a kinetic friction, which means we can take our calculation of forces, and rather than duplicating work, we'll use our calculator trick and store this result in our calculator. But now we know we have motion, so we have to complete the motion consideration. So looking at our problem, we're asked if the car will reach the bottom of the hill. One of the ways you might consider approaching this is to determine if it has an initial velocity, what is the final velocity when it's at the bottom of the hill? Knowing that we have an equation for acceleration already, we could start with velocity final squared is equal to velocity initial squared plus 2 times the acceleration and the displacement, which means you can solve for velocity final by taking the square root of that same term. We have to be careful to consider our directions, so we have an initial velocity down the ramp, which would be negative, and that gets squared. And then we're going to add that to 2 multiplied by our acceleration, which is stored, and it's positive, so we don't have to apply any changes to the sign. And we have a change in position. So if the car starts here and moves this way 12 meters, that's in our negative x direction, so we have to include negative 12. I'll pause for a moment here and let you enter this in your calculator. And your calculator should come back saying that we have an error, which is interesting. I understand that as students, you may look at this error and consider that you've entered the value in your calculator incorrectly. And while this does happen, this is why we need to be confident in our use of our calculators, and we need to practice to avoid those errors in situations where they are false errors. This error is in fact the correct interpretation of our scenario. So we need to consider another approach to this question. So let's look at motion part 2. Instead of asking, what is my velocity at the bottom of the hill? Let's find out where we run out of velocity. So in this case, we're going to say velocity final equals 0 meters per second, and we're going to ask where does that happen? And with that value, we will interpret the answer to our question. If the number is anything greater than negative 12, we know we've reached the bottom of the ramp. If it's anything less than negative 12, then we never reached the bottom. So which equation do we use? Well, we can start from the same equation and this time rearrange for displacement. And we can substitute our values. Again, reusing our value from acceleration calculation previously. And this time, we should get a result of negative 0.939657 meters. Saying that from where the pedestrian bumped into the car, it moved less than a meter. Our interpretations of this value is that no, the car will not reach the bottom of the hill. So what do we see? Sometimes it's important to think of a creative way to approach the question. One of the other things we should note is that we didn't change our steps. We still had a system of equations. But because we were able to come to this calculation early, and rather than reduplicating the work, our system came from substituting that stored value rather than the whole part of the equation that we had. And of course, as you saw, we still did evaluate our information. So you see, we've taken our understanding of ramps from the previous problem, which often revolves in how do we decompose that weight vector. And now we've combined them with our understanding of frictional forces. And again, we're trying to connect motion to that net force using the same approach. And we're going to introduce another class of problem. We're going to start talking about pulleys in this course. When we apply a pulley to a problem, we're attempting to do one of two things. We are either trying to change the direction of the force from the vertical plane to the horizontal plane, or we can be attempting to multiply a force. For this unit, we are going to concentrate on the first type of problem, changing the plane that a force acts in. So if a pulley connects the forces acting in two different planes, it will also connect the motion in the two different planes. We solve these problems with a similar strategy to projectile motion problems. But in this case, rather than connecting the two portions by time, we connect the two portions by acceleration. One thing to consider is that the string ensures that the acceleration is constrained, meaning that it won't necessarily be equal. If we look at our diagram, we would have an x-axis working horizontally and a y-axis working vertically. If there's enough unbalanced force that this block can move down, the string ensures that the block on the table will move right. Reflecting on our current chapter where we talk about the acceleration is the result of an unbalanced force, we're talking about the acceleration of these two blocks. The block on the table will accelerate in the positive x direction, while the block hanging on the string will accelerate in the negative y direction. So the constraint that we have is that the acceleration in x will be equal but opposite to the acceleration in y. And that negative sign will be very helpful in many of our problems. Next week, you're going to read chapter 6. Consider the sample problem 6.4 from the textbook. Now, the textbook shows the best approach to solving this problem, and I'm not reviewing it to change that idea. But I do think it's beneficial to look a little closer at several of the steps. The textbook follows all of the same procedures. Step 1, draw free body diagrams. Note, in pulley problems, we have two objects, so we draw two free body diagrams. In this case, we have a block and it has a mass, but because the textbook tells us that this is a frictionless table, we have no need to consider the weight and normal forces on this block. Our focus is entirely in the horizontal direction, so we know we will have a force of tension acting in that direction. Let's switch our focus to block B. Block B has a mass, and because our focus does include the vertical direction, we will include the weight of this block. The other force acting on this block is the force of tension. The force of tension in the string anywhere is the force of tension in the string everywhere. So these two red vectors are equal in magnitude. Let's move on to our consideration of the forces. In block A, we set up Newton's second law, saying that the sum of all the forces will be equal to the mass and the acceleration of block A, and the only force present is that force of tension. What about the forces on block B? Again, the sum of all the forces will tell us the mass of block B and the acceleration of block B, and it has a force of tension and it has a weight. We can replace that weight with the way we know to calculate, so that'll be the mass of the block times the acceleration due to gravity. And we'll follow the textbook suit and we'll use the method where we rearrange both of these equations for the same quantity, and then we set the equations equal to each other. So let's look at that system now. The reason that we're skipping step 3 is that the question asks us solely about the acceleration of the system, meaning we don't really need to consider any other motion equations. Once we solve for acceleration, we'll be done. So setting our equations equal to each other, we will have the mass of block A times the acceleration of block A is equal to the mass of block B times the acceleration of block B minus the mass of block B times the acceleration due to gravity. Now you may look at this equation and realize we know the mass of the blocks, we know the acceleration of gravity, but we don't know the acceleration of each block. The question asks us to solve for the acceleration of block A, and we only have one equation here, so we need to make sure we only have one unknown. We're going to apply the Pulley constraint. Because I don't want to know the acceleration of block B, but I know these two are connected, I'm going to replace acceleration of block B with negative acceleration of block A. And with that consideration, we can remove the vector signs from these arrows because we've added the signs to them. So this will give us the mass of block A times the acceleration of block A is equal to the mass of block B times negative acceleration of block A. Subtract the mass of block B. And because we've removed the vector considerations of these accelerations by adding the sign, we'll do the same for here. And we'll say that this is negative g, which means we can simplify all of our negative signs, meaning that we have a single negative sign on this term, and we are going to subtract by a single negative sign on this, term. So this will become positive, and this will become negative. Simplifying, we have mass of block B, gravity, subtract mass of block B, acceleration of block A. This application of the constraint is something that I think the textbook glosses over too quickly, and one of the main reasons that I wanted to take a deeper look at this problem. The other was to make sure that this step from here on is explained in more detail. The textbook explains this as, the rest is just algebra. Let's look at that algebra. My goal is to get the acceleration of block A alone. So I need to get any term with that variable on the same side. This term is subtracted from the right, so I'm going to add it to both sides. Now by looking at the left-hand side, I have two terms that share this acceleration of block A value. Like the previous problem, I'm going to apply factoring, which means I can take that A outside and multiply it by the mass of block A and mass of block B, all in brackets. Last question, we factored so that we could simplify and cancel things out. On this question, factoring means that we can take this term that's multiplying against our variable of interest and divide it from both sides. Now that we are completely rearranged, we can substitute our values, and we should get an acceleration the same as in the textbook of 5.64 meters per second squared, positive and acting in the horizontal plane. So we have an acceleration of 5.64 meters per second squared right. This problem highlights the importance of understanding the acceleration constraint caused by a pulley and string, and the importance of being very comfortable with all of our algebra steps, including factoring. One of the conceptual things that arises here is an understanding of how these objects move. Block B has a weight and is free to move. Without the string, it would fall as a previous free fall problem. With the string, it's connected to another mass, and that mass will reduce the amount of motion. So note that part of this calculation is finding the net force on both objects and applying that to the combined mass of both objects. So net forces on systems of objects apply to all the mass in the system. It would benefit you to consider how we can combine pulleys with friction, ramps, and motion phases of problems. In fact, we'll make one of those combinations now. Let's consider two blocks with mass connected by a string and pulley, and the block on the table now experiences friction. The coefficient of friction between the block and the table is 0.35. And this question asks us, is the system in equilibrium? We'll go through the same process again. Let's begin with our free body diagrams. I'm going to call the block on the string block B and the block on the table block A. And we'll begin with block B this time. So we have our block. It will have a weight and it will have the force of tension from the string that connects it to block A. And block B is done. Now let's consider block A. Our previous problem had a frictionless surface, so we didn't consider the weight and normal force. But because this block experiences a force of friction, we need to consider both the weight of block A and the normal force that block A experiences. And block A will also have the force of tension applied. This means that our consideration of the forces is slightly more complex this time. In block B, we set up the sum of our forces, setting it equal to the mass of block B and the acceleration of block B, and our forces will be the force of tension and the weight. I'm going to apply what we know about the weight and the constraint on the acceleration to say that we will end up with subtract the mass of block B times the acceleration due to gravity. And here we've received this negative sign by taking the vector off of our gravity, so that's our negative. And this is equal to negative of the mass of block B multiplied by the acceleration of block A. So here we've applied the acceleration constraint due to the string. To try and keep this approach as similar as possible to the more simplified problem, we'll also set this equation equal to force of tension, which means rearranging we'll have the mass of block B times gravity, subtracting the mass of block B times the acceleration of block A. And we switch our focus to the forces on block A. Again, we want to set up the sum of all forces will be equal to the mass of block A times the acceleration of block A, which means we will have the force of tension plus the force of friction is equal to the mass block A times the acceleration of block A. And we have to do some consideration about that force of friction. You may recall, force of friction is equal to the coefficient of friction multiplied by the magnitude of the normal force. Also, the normal force is equal to negative the weight. And we know this because the object is going to stay on the table. It's not going to suddenly gain an acceleration up or down, which means that the force normal will be equal to negative of mass times gravity, which means in our case, it will just be mass times gravity after we take out the vector consideration of gravity. We had a negative 9.8 and a negative on the symbol. So that's how we end up with a positive value. So our force of friction will be the coefficient of friction multiplied by the mass of block A and the acceleration due to gravity. And the last thing we have to do is be careful, because when we work with friction, we have a calculation for the magnitude of the force, and we have to interpret the direction. We're going to interpret right as positive. So that means our friction acts in the negative direction. So when we substitute, we need to take that into consideration. So we'll have the force of tension acting in the positive direction, subtract the coefficient of friction times the mass of block A times gravity is equal to the mass of block A times the acceleration of block A. And in this field, or in this plane, that will be a positive value. Rearranging for tension, we get that the mass of block A times the acceleration of block A plus the coefficient of friction times the mass of block A times gravity. And now we consider the system, setting these two things equal to each other. Again, you may have noticed we skipped over the consideration of motion. And again, that's because when we solve our system, we'll solve for acceleration, and we have no further considerations here. You may notice that we have two common symbols. Gravity shows up on both the left and right side, and acceleration shows up on both the left and right side. I'm going to try to collect all these terms. And apply our factoring step so that we can isolate A. And we'll see that we have an equation with one unknown now, so we can switch over to our evaluate step. So substituting all our values and calculating, we get positive 2.167307 and a few more pieces of information. And we just want to make sure. So we were solving for the acceleration of block A. So having a positive value in the way we set up our system says that block A accelerates towards the pulley, and we can accept this value. Note that if we had applied the constraint of acceleration way back here to instead solve for B, we would have ended up putting a negative B in here. We would have ended up with a negative value here, which would have told us that block B accelerates down, which also would have been an acceptable answer. You need to be careful though, because if you get confused about where you apply that negative sign and try to say that B accelerates up or A accelerates left, this is not possible. The weight of B is the motivating force in this problem, and the friction on A only serves to reduce the amount of acceleration possible. So to answer our question, the system is not in equilibrium. Before we move on to talk about the third type of problem that Chapter 6 introduces, let's look at a little bit of physics in the current news. Later this week, NASA's Perseverance mission, as part of the Mars 2020 mission, will reach the planet Mars. As the landing craft enters the atmosphere, it'll begin what NASA considers the 7 minutes of terror approach. This is where the spacecraft transitions from hurtling towards Mars to begin trying to lose all of its velocity in order to safely set the rover down on the surface. This happens in several stages, and you can see some of that information on the screen now. Any one of these segments of time, whether it's the entering the atmosphere and using air braking from the air resistance, or deploying a parachute to amplify the air resistance and lose velocity, or even the final stage where JPL will deploy a sky crane method similar to that from the Curiosity mission in order to gently set the rover on the ground at a maximum velocity of 0.75 meters per second. Notice that in a span of 7 minutes, these stages are able to remove more than 5,000 meters per second, or 5 kilometers every second of velocity. We're going to use just that last powered descent stage to look at what the textbook refers to as lander problems. Lander problems are asking us to look at a situation and determine the force required to reach our desired motion. So we know what kind of motion we want, and now we're going to calculate the force, which is reverse to the previous types of problems. We still want to look at our system and draw a free body diagram. And in this situation, we will have the lander and rover's weight on Mars, which will be calculated similar to the way we calculate it on Earth, but now you'll have the mass times the acceleration due to gravity on Mars, which you saw on the previous page was approximately 3.72076 meters per second squared, or 1/3 of the acceleration on Earth. Our goal here is to determine the amount of thrust we need to induce our desired motion. One of the reasons that NASA uses a powered descent phase as the last phase is because the Martian atmosphere is so thin that there's not enough drag or not enough wind resistance to slow the craft down. Here, we'll just treat the wind resistance as negligible. Moving on to our second phase, we consider the forces. This consideration is still the sum of all of our forces, which is the force of thrust plus the weight, and that's going to tell us how to get our mass of our rover to accelerate as desired. While we don't know many of these quantities, we can start to put in consideration of their direction. So our force of thrust will have a magnitude in the positive direction, and we'll have to subtract from that, because it's in the negative direction, our mass times the gravity due to Mars, and this will be equal to our mass times our acceleration. Remember, our rover is moving down, which will be a negative displacement with a negative velocity, but the whole time that velocity is getting smaller, which is the equivalent of having a positive acceleration. I'm going to rearrange this equation for thrust, and we can do some factoring just to simplify the equation. But at that point, we're stuck as we have one equation with two unknowns, the amount of thrust we desire and the acceleration we need. So now we switch our focus to motion. So in this case, we know that the Mars rover leaves the parachute phase with velocity of negative 85 meters per second, and this phase begins at a height of 2,100 meters, and it will end with a reduced velocity of negative 0.75 meters per second at a height of 20 meters above the surface. And we can note that the mass of the lander and the sky crane is equal to 2,095 kilograms. Well, 400 kilograms of that mass is fuel, which would be burnt off during the descent. We're going to treat the vehicle as a constant mass. So we know an initial velocity, a final velocity. We have two heights, which will give us a displacement, and we're looking for acceleration. Whenever we are considering change in velocity without understanding of time, we can use our velocity final squared is equal to velocity initial squared plus 2 multiplied by acceleration multiplied by displacement. We'll rearrange that for our acceleration. And with that, we're done setting up our motion equation. And we can move on to the system phase. So we take our equation for the amount of thrust we require, and in place of our acceleration, we'll substitute the velocity final squared rearrangement. Remember that you also have that component of Martian gravity, and we can substitute and evaluate. And plugging all of these values into our equation and calculating, we should get an average thrust requirement of 11,433.2606 newtons, which is approximately 11,000 newtons based on the inputs that we had. And while you didn't have access to this information, you should note that the sky crane has 8 engines, each capable of 3,000 newtons of thrust, meaning that we have roughly 24,000 newtons of thrust as our maximum value, and our average is well within that. You should be able to see that just to keep a constant velocity, we would need to have enough thrust to match gravity, and then to induce acceleration, we need to have more thrust than that. So our total thrust value includes enough acceleration to do what we want and overcome the acceleration due to gravity. There's a second part. What happens to the sky crane the moment it lets go of the rover? Well, we know that the sky crane is applying thrust of approximately 11,000 newtons, and it was applying that to the entire mass of both the rover and the lander. But the moment it lets go of the rover, it now has a smaller mass. The mass of the sky crane itself was 1,070 kilograms. And by the time it reaches the point where it is about to let go of the rover, it's burnt through the majority of its fuel. So of those 400 kilograms, it's likely down to about 700 kilograms total mass. The mission plan is actually to allow the sky crane to let go of the rover and use its remaining fuel to vacate the area and launch as far away as possible. So because Newton's second law tells us that force is equal to mass times acceleration, if our force stays the same and our mass gets smaller, then our acceleration will have to increase, meaning that the sky crane's velocity that was negative 0.75 meters per second will very quickly become a positive value, accelerating it away from the rover until it runs out of fuel, at which point it'll begin to crash back down towards the Martian surface. As we move forward, we will begin to combine all of these components of motion. So while we only looked at a few scenarios today, you could have any combination. And you will in fact see that your textbook has questions that take free-falling objects and pulleys and ramps and frictions all in the same problem. This does not change your approach. We will still use the same 5 phases. The key skill to solving more dynamic problems is being able to concentrate on the phase you are in. Each phase that we went through let us apply the specific concept we've already covered. So when we look at a problem, we draw free body diagrams. And we draw multiple free body diagrams. And one of the ways that we think about the forces in our problems is that we concentrate on applying Newton's second law. And one of the tricky conceptual features here is that this sum of forces often gets replaced with force of tension and weight and friction in some combination depending on our scenario. Because our problems are beginning to be more dynamic, we consider the forces phase of our setup and the motion phase of our setup separately. And the motion phase applies our equations of motion. Our problems can be as simple as looking for acceleration, or take on multiple levels of more complexity by considering other concepts of motion. It's essential to understand that the connection between these two phases is acceleration. In order to be able to solve any calculation, we need to set up a system of equations. And our systems showed up in 2 different situations. Our systems could connect force and motion, or it could connect forces on multiple bodies. And as we saw, we could have a problem that we have to do both of those sets of systems. Our substitute and evaluate phase could have taken 2 different forms, either where we have a value that we've calculated and stored in our calculator and reused, or as I suggest, that we substitute all values and calculate once. The other thing that we need to emphasize here is that this stage always includes an interpretation of your value to make sure we understand which quantity we're talking about, whether or not that value is actually possible, and whether an error is actually the correct response for the equation we've set up. This week, I'm going to leave you with our most difficult think about this to date. 2 skiers slide up 2 different slopes, one at 5 degrees and one at 15 degrees. Both skiers enter the slopes at 5 meters per second. Which skier will travel the greatest total distance? You will find it necessary to know that the coefficients of friction are 0.05 for kinetic and 0.14 for static, and these are between the materials of waxed skis and dry snow. We can also make the assumption that the skiers are traveling slow enough to ignore air resistance. I'm going to give you a hint here. Set the bottom of the slope as 0 meters and consider whether each skier will have multiple phases of motion. Look at whether the skier will travel up the ramp as described, down the ramp, or even consider moving after leaving the ramp again. I'm going to put the free body diagrams for the initial phase on the screen and let you work from there. Recapping our lecture, this week we extended our knowledge to apply both force and motion to more dynamic problems. We reiterated that we always want to approach problem solving with a systemic method. We concentrated on breaking problems up into multiple phases, whether that was the force phase and the motion phase, or whether that was different phases based on motion. We saw that our key strategy here was to apply Newton's second law to connect a force phase with a motion phase. And this is our first grouping of problems where we have multiple bodies and consider them as a system. We actually look at a lot more of these when we go on to work and energy in Chapter 7. And because you waited until the end, and this is the most difficult problem, I'm going to also include the answers to the Think About This problem.